For decades, it was the symbol of luxury air travel, a true giant of the skies. But then, in just about 35 seconds, it became a symbol of unimaginable disaster. So today, we're going to put on our detective hats and use a little physics to conduct a forensic investigation into the final moments of the Hindenburg to find out what really happened. So let's set the scene. It's May 6, 1937, over Lakehurst, New Jersey. The massive German passenger airship Hindenburg is getting ready to dock when it just erupts into a massive fireball. This unbelievable moment was captured in this iconic photograph and, of course, immortalized by the voice of radio reporter Herbert Morrison, whose shaken exclamation, "Oh, the humanity," really conveyed the absolute horror of what he was seeing.
For almost a century now, that's been the question. Was it sabotage, a freak lightning strike, or was the cause hidden in the very science that allowed this colossal machine to fly in the first place? All right, let's follow the evidence.
To understand why it fell, we first have to understand how it stayed up. And the answer isn't some big mystery, it's pure physics, with principles that go all the way back to ancient Greece. It all comes down to Archimedes' principle. And to put it simply, for an object to float in a fluid, and you gotta remember, air is a fluid, it just has to be lighter than the fluid it pushes out of the way. So for the Hindenburg, this meant the total weight of everything, its structure, its engines, its crew, and the gas inside it had to be less than the weight of the enormous volume of air it displaced.
And this brings us to a really critical choice: the lifting gas. Now, the original design called for helium, which is completely non-flammable and safe. The problem was, at the time, the United States had a global monopoly on helium, and, with political tensions on the rise, they banned its export to Germany. This forced the Germans to use hydrogen instead. Now, hydrogen actually provides more lift, but it came with one catastrophic downside: it's incredibly flammable.
So, now that we've got the physics down, we can take a closer look at the machine itself and the chain of events on that day. Because this wasn't just any old airship. For its time, it was a technological marvel.
The Hindenburg truly was a great floating palace. I mean, at over 800 feet long, it dwarfed modern jumbo jets. Inside its rigid frame were 16 massive gas cells holding 7 million cubic feet of hydrogen. And its outer skin was basically cotton, treated with chemical compounds to make it taut and reflective. For its time, it was the absolute peak of luxury travel.
After being delayed by storms, the Hindenburg finally got to Lakehurst. But the bad weather wasn't quite done with it. A sudden shift in the wind forced the commander to make a really tight S-turn to line up with the mooring mast. This was not a standard maneuver, and it's a critical moment because many believe this sharp turn put immense stress on the airship's frame.
And what happened next is a huge clue. During that turn, the crew noticed the ship was becoming dangerously tail-heavy. To fix it, they had to drop almost a ton of water ballast from the back, and they even sent 6 crewmen running to the front of the ship to act as human counterweights. This was a clear signal that something was very wrong in the tail, most likely a major leak from one of the hydrogen gas cells in the rear.
So now you have the perfect conditions for a disaster. The ship was grounded by its mooring lines, which creates an electrical path to the Earth. It had just flown through a storm, building up a massive static charge. So we've got our source of ignition, a static spark. But what did that spark actually ignite? Well, this is where the investigation splits into 2 big competing theories.
So in one corner, we have the classic theory. The spark ignited all that leaking hydrogen. In the other corner, you have a more modern theory from the 1990s, that the skin of the airship itself, coated in what was basically rocket fuel, was the real source of the fire. Let's look at the evidence for both.
The evidence for a huge hydrogen leak is pretty compelling. You have eyewitnesses on the ground who said they saw the fabric fluttering near the tail, a classic sign of a gas cell rupturing inside and pushing against the outer cover. And that sharp S-turn? Well, that gives us a potential cause. A bracing wire could have snapped under the strain and sliced right open a gas cell.
But in the 90s, a new idea came along: the incendiary paint theory. A former NASA engineer named Addison Bain pointed out that the chemical dope used to coat the fabric had stuff in it like aluminum powder and iron oxide. Incredibly, those are basically the same things you find in solid rocket fuel. Bain's shocking conclusion was that the skin itself was flammable enough to have started the whole disaster.
And the visual evidence for this theory is pretty striking. On the left, you've got a modern lab test where a replica of the Hindenburg's fabric is lit on fire. On the right, a photo of the actual disaster. The color and the way the flames look are remarkably similar, which seems to support the idea that the skin burned first. But, looking similar isn't the whole story. And this is where physics gives us the final answer. Researchers recreated the exact fabrics and put them through standardized burn tests. The results are undeniable. As you can see from this data, the fabric, while, yeah, it's flammable, burns incredibly slowly. To burn the full height of the ship would have taken almost 2 hours. We know the Hindenburg was destroyed in 35 seconds. The math just doesn't work.
So this leads us to the most likely conclusion. The incendiary skin might have been the initial spark, the match that lit the fuse, but it couldn't have been the main fuel. Only a massive, leaking volume of hydrogen mixed with air can account for the terrifying speed and scale of the fire that consumed the entire ship in just 35 seconds.
The Hindenburg disaster brought a swift and dramatic end to the age of passenger airships. But the dream of lighter-than-air flight didn't die in those flames. In fact, the lessons learned are actually shaping a whole new generation of these aircraft. I mean, the tragedy created this deep-seated public fear of airships, but engineers and visionaries, they never forgot the incredible efficiency of buoyant flight. They just needed a new, safer way to do it.
And the modern answer is the hybrid airship. The concept is really cool. It combines the best of both worlds. It gets most of its lift from a buoyant gas, but it also uses aerodynamic lift from its shape as it moves through the air, just like an airplane wing.
There are two main types being developed. You have dynostats, which are shaped like giant wings and are designed for really efficient, long-endurance flight. And then you have rotostats, which actually use rotors like a helicopter, which makes them incredible flying cranes that can lift massive payloads straight up.
And modern airships, like this one, the Airlander 10, have learned the most important lesson from the Hindenburg. They fly with helium. Safe, stable, completely non-flammable helium. The single greatest flaw in the Hindenburg's design has been totally engineered out of its modern successors. And that leaves us with a fascinating thought. These new airships promise to lift ultra-heavy cargo with just a fraction of the fuel used by traditional aircraft. So, could the legacy of the Hindenburg, a story of fire and failure, ultimately be the thing that helps us build a more sustainable future in the skies? It seems the dream of a floating palace is, once again, getting ready to take